Hi, welcome to Thinking Spatially, the third and final introductory video for Ms. Moser's physics class at Beaver Local. Okay, as with all the other videos, I recommend that you take some notes. There's a quiz that follows linked at msmoser.pbworks.com, and there will be some follow-up questions on the first day of school for all three videos. Let's get started. When we're thinking about objects spatially, especially in the context of physics problems, we have to view them a little bit differently. Let's take this loaf of bread, for example. Yes, a loaf of bread. If we're going to think about this spatially, we need to reduce it to something that's a little bit more regular and more of a simple geometric shape, such as a rectangle with dimensions that approximate those of the bread. Now, this is something that we can easily compute a volume for, we can compute densities for. It just makes dealing with the loaf of bread easier if the bread is really a rectangle. Okay, let's look at some other geometric approximations. This grossly oversimplified physics person can also be approximated. We can take all the complexity that makes up a person and approximate it with a cylinder. That's right, when it comes right down to it, we're all just cylinders. Okay, so these are some ways to approximate physical objects that make it easier to approach problems. I'll give you one more. Think about it on your own. What about a garden hose? How could you approximate the crazy shape of a garden hose to make it into a simple geometric solid? Ding, 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 ding. Feel free to press pause if you need more time. I'm about to give away the answer. Ta-da! It's another cylinder. Now, of course, I wasn't able to fit the entire length of this cylinder onto my picture, but yeah, when you break it down, all the garden hose really is a very long cylinder. Okay, now that we've got things visualized as simple geometrics, we want to think about the dimensions of the object and what facet of the shape best approximates what. So, for our person, let's start with that. It's fairly simple. The height of our cylinder would be equal to the height of our person. Okay, what would we use for the diameter of our cylinder? Well, there are a couple approaches. We might take the width of our person's shoulders and assume that that's roughly the diameter of the cylinder. We might take their waist measurement and assume that that's the diameter of the cylinder. We have to come up with something that roughly approximates it. Either of those could have a case made for it. It's up to you to choose the one that's most appropriate, and we'll talk a lot more about that when we all get into class together. Okay, what about the garden hose? This one should be pretty easy. Well, we know that the length of the hose, once it's uncurled, would be the height of our cylinder, and we know that the diameter of our hose would be the diameter of our cylinder. Okay, the bread is probably the simplest, because the height, width, and length of the bread will directly correspond to the dimensions of our solid rectangle. Okay, now that we've got these, let's think about doing these sorts of geometric solids in the context of problem solving. Let's talk about donuts. Donuts. Okay, so we have a donut as an object. Let's say, furthermore, let's say that this donut and a whole bunch of its best friends are about 15 centimeters wide and about 5 centimeters high. That's a nice little donut. They've got a hole in the middle, but we're not even going to concern ourselves with how big the hole in the middle is. Now, here's the problem you have. You have been drafted to fill a box with donuts. Are you ready? It's a 1 cubic meter box. This is going to be a lot of donuts. I hope you have hungry friends. So, how do we begin to approach this problem? The first thing to do, and I've kind of taken this step for you, is always to visualize the situation and draw a picture. So let's make a simple geometric approximation of our donut. Well, what's a donut? It's really, you guessed it, a cylinder. And in this case, the height of our cylinder is 5 centimeters, while the diameter of our cylinder is approximately 15 centimeters. There are a number of ways to approach this problem, so let's go with a couple of the simplest. The very simplest way to do this might be to take the volume of the box and divide by what? The volume of a donut. Now, this would assume that the donuts pack in perfectly, that all of their volume is going to meet in the box, and of course that's not the case. They're not perfect little cubes that are going to go into the box perfectly, but would this give us a rough approximation of how many donuts we could fit in the box? Sure it would. This might be the quickest, dirtiest way to do it. Alright, let's continue down this road then. We know that to find the volume of a cylinder, we take pi r squared times the height of the cylinder. In other words, the area of the circle multiplied by the height of the cylinder. Okay, let's get to work. Okay, so we have our formula for the volume of a cylinder. Volume of a cylinder is equal to pi r squared, times the height, and we can go ahead and multiply through here and get the volume of a cylinder. Now let me ask you this. When we get the volume of our cylinder, what units will it be in? Well, if we follow the logic here, it will be in cubic centimeters. Okay, that's fine. What units is the volume of our box in currently? It's in cubic meters. Do we have a problem? We kind of do. So there are two routes we can take. We can convert our centimeters into meters from the get-go, or we can get our volume and then convert our volumes so that they match. We'll do it the easy way first. Let's convert our centimeters from the start. Okay, through a little fancy footwork, we got our conversion for the diameter and hence the radius. We got our conversion for the height. We used those numbers. Be careful about order of operations for your diameter division to radius. And we multiplied it all together. Whoops, that's a preliminary number. Times pi. So when we finish it, we find that the volume of our cylinder, or our donut, is 8.835469 times 10 to the negative fourth cubic meters. Okay, now all we have to do is divide that into the volume of the box. Okay, our calculations give us a total of 1,131.8 and a whole bunch of numbers after that, donuts, that we think we could fit in that box. Now, this is a rough approximation. How many uncertainty digits do we have? How many sig figs do we have? If we look back at the height of our donut, it was 5 centimeters, and the volume of our box was 1 cubic meter. So what we're really saying is that we think we could fit about 1,000 donuts in that box. It's a lot of donuts. Okay, now let's remember some things about doing conversions. What if you had gone ahead and gotten your cylinder volume in cubic centimeters and you needed to convert it, or the volume of your box, into cubic meters? How would that look? Let's do a practice on the next slide. We'll start with some just random numbers here. A 350 cubic centimeter object has what volume in cubic meters? So let's think carefully before we get too excited. We're going to do a straight up factor label conversion, just like we always have. So we start in the first box with, of course, our given. You knew that. Now, we know that we need our units to match. And we know that whatever we want to end up in is going to have to be in the top box. This is a one-step process. So we're going to put cubic meters right up here. Okay, what's our conversion factor here? Well, we know that if we were converting centimeters and meters, we would use 1 centimeter is equal to 1 times 10 to the negative second meters. Is that true in this instance? No. Because if we think about a 1 cubic meter box, that is a box that's 1 meter wide, 1 meter high, and 1 meter deep. There are 100 centimeters here, there are 100 centimeters here, and there are 100 centimeters here. So 1 cubic centimeter is equal to 1 times 10 to the negative second meters cubed. That's really important. And it's not that hard to just write that into your factor label. That's actually what I typically do. It looks like this. This is how it looks. Note that I've done the conversion up here to make my math easier in the end and changed 350 to 3.5 times 10 to the second. When I multiply this all out, what I get is 3.5 times 10 to the negative fourth cubic meters. Our cubic centimeters cancel, and we have meters times meters times meters. Cubic meters, that's what we wanted. So, just other points to think about when looking at a problem and thinking spatially and making sure that your units are all lined up. Let's list some general steps for problem solving in physics. The first thing you want to do when presented with any physics problem is to visualize the situation and draw simplified representations of the objects you're talking about. Hence, our donut becomes a cylinder, our garden hose becomes a cylinder, our loaf of bread becomes a rectangle. This is a very good first step, and it's a good step to get into for the rest of the year, for all the stuff that we'll do in physics. Okay, what's our second step? Label, label, label. I can't stress this enough. Not just labels, but units. Numbers, units, arrows and lines to show what dimension we're talking about. For example, our donut. So, I've got numbers, I've got units, and I've got some lines that indicate what dimensions we're talking about. When I drew my cylinder, all those things transfer. Our third step should always be to check our units and convert where needed. We notice right off, if we do this step, that our donuts and our big box are in different units, and we save ourselves a whole lot of time and hassle if we do the conversions right then, rather than having to go through and do a conversion in volume, which is a cubic measurement, and you're much more likely to screw it up. Then, and only then, you can start to list your variables, write and select formulas, rearrange, and plug in actual numbers. Once you've done all those, there's one important last step. That is to check for reasonableness. So, we look at the answer that we got for our donuts in our box. We say about 1,000 donuts can fit in a box. Does that sound reasonable? Sure. If you had come up and said that 10 donuts could fit in a box, I would seriously doubt you. If you had said that 4 million donuts could fit in a box, I would seriously doubt you. So, that's where using more than one approach to solve a problem comes in. We use the simple, quick, and dirty. That might actually be our reasonableness check, and we might go for a more specific number and use the two to compare. If we get vastly different numbers, orders of magnitude different, when we solve a problem using a quick and dirty estimation approach and using a more specific, precise method, we have a problem. Okay. That's it, folks. Go take your quiz. Enjoy the rest of your summer, and I'll see you in a few weeks. If you have any questions, please feel free to email me. You've got it. And this is going to be the shortest of your quizzes. Real simple with a few follow-up questions for you at the end. Okay. Take care, and I'll see you soon.